I'd like to introduce our panel group here. Mr. William Orme from Orme, Strategic Marketing Manager. Thank you very much. Mr. Brian Choi, Samsung Electronics, PhD, Principal Engineer. Thank you, Brian. And Nick Heaton, Distinguished Engineer with Cadence Design Systems.
Hello. Good afternoon, everybody. Thanks for coming along. So before we get started on the discussions, I thought it was worth just explaining who we are and what we do in our day jobs, so you get a feeling for the angle, and our background to this panel discussion. So I'll start with myself, because I've got the microphone. Hard luck, Nick. Yeah. And then we'll go to Brian, then to Nick. So William Orme, I've been at Arm about 19 years, and before that I've had stages as hardware design engineer and stages as a software engineer, and now I find myself looking after mainly our interconnect products, looking at how to develop those, and that's a sort of fabric that spreads across the SOC and gets very involved in a number of key design challenges, particularly the configurability of IP and the way that that can be deployed effectively. So I was very involved in the evangelization within ARM for last year's announcement of the acquisition of a company called Dulog, which had got some very useful technology for this. So that's me. So over to Brian now.
Thank you. Okay. So I'm Brian Choi. Right now I'm a principal engineer at Samsung Electronics in Korea. And then my daytime job is basically SOC integration. So I build and architect all the Galaxy-based SOC. And I joined Samsung about 1 year ago. And then my previous life, I was SOC architect at Intel Corporation about 11 years. So recently, my main focus is that how we build the SOC faster, because our design cycle is shorter and shorter. So that's my main focus. And then also how we actually validate faster and efficient. And then that's pretty much it. Nick?
Thank you, Brian. So I'm Nick Heaton. I'm a distinguished engineer with Cadence R&D. And my day job is really to do with architecting and innovating new products in the SOC space. My background is I was a designer for about 15 years and then went into verification, advanced verification with Veracity. And about 5 years ago, we took a step back and looked at a lot of you probably aware of UVM as a methodology for verification, and we saw that verification had sort of starting to mature, and we took a step back and looked at what the additional problems customers were having, and repeatedly with our big customers we were hearing integration was a big challenge. SOC integration, how do we address it? And so basically the last 5 years I've been looking at new products or taking existing technologies and applying them into this space, trying to understand the challenges and apply those technologies. So hopefully I'll share with you some of the experiences of what the customers have told me and the kind of things that Cadence has been looking at in conjunction with ARM and Samsung to try and figure out where the pain points are, what the technology needs to do to be more applicable in that space. So hopefully this will be interesting for you.
Thanks, Nick. So we're going to sort of split this panel session into sort of three areas, and I'm hoping that the audience here can, contribute and ask questions and, bring out issues as we go through this. It is a panel session after all. So we're going to start off with the challenges of SOC design, and just to get the ball rolling, I've got a few items here that I've picked up through talking to our customers about, how they some of the challenges, and I'm going to be sort of giving you the sort of IP provider's perspective, and then I'm going to hand over to Brian to give you the real perspective from a sort of somebody who actually has to do this for their real job. So I mean, clearly, the complexity is always on the rise. More components, more connectivity, and one of the sort of common themes that we're spotting is that a lot of people are dividing those larger systems into subsystems, modular subsystems, so they can get a subsystem reuse. And the composability and the decomposability of designs is a key trend moving forward, which allows reuse and may help to localize some of the timing closure issues. And I was going to also draw on some of my interconnect experiences here. Sort of these are things that cross the entire SOC. And here we're looking at the interconnect sort of come of age, as it were, and has to deliver a lot more than just connectivity of the bus, as it were. So it's really about provision of a lot of services, and the first provision, I guess, is quality of service, thing that really kind of matters, and that's guaranteeing low latency for the masters that need low latency, like CPUs or whatever. But other quality of service guarantees can be about bandwidth, throughput capability, or even not exceeding maximum latencies for some of the real-time masters, so things can be met. I guess the rise of multi-core heterogeneous designs means that we've fundamentally got a coherency issue to deal with, as to improve performance. Processors and so forth are keeping local copies in cache and so forth, which leaves the interconnect responsible for maintaining coherency across the different processors, big little CPUs, GPUs, I/O coherency for the I/O devices. Virtualization of the memory map, so software can see an idealized scenario, and that can be mapped either for separating out different sections of the software so they don't interact with each other, sort of so-called sandbagging, or just for dividing up the memory map as appropriate. An isolation of the software from the hardware, a separation. Security, obviously a big thing, particularly in IoT, but also across all designs, where trust zone technology from ARM helps there a bit. And clock and power management being a big thing, obviously for power saving. The division of the SoC into lots and lots of different clock and power domains to exploit power saving takes a lot of control. And the physical awareness, the layout is something we see a lot of in the configuration of an interconnect IP. It needs to be aware of where it's going to end up with the ideal design for your interconnect. And of course, if only things work perfectly first time, so debug and trace of any system is obviously a key part in getting there. So those are some of the issues I've seen, and I'm going to pass over to Brian now as a customer to give us the real bird's eye view of what's happening.
Thanks. So from Samsung's perspective, when I see it so I have two companies I worked on. So Intel is one example. The other one is actually Samsung. And if I look at the design cycle, so Samsung's design cycle is a lot shorter. I mean, I cannot tell you how much, but and then also, if you look at the Samsung smartphone, basically we have two premium smartphone every year. And then, not to mention that we also have a lot of the medium or low-end smartphone. And then we have a SoC for that too. So we have a lot of SoC internally. And then, but the design cycle is a lot shorter than my previous company. So
Bring the mic closer to your mouth.
Oh, sorry. So from Samsung's perspective, the biggest challenge is actually the design cycle. How we reduce the design cycle for each SoC. And then, so since I joined Samsung, we are looking at the what is the better methodology to actually enable fast turnaround time and then fast validation and all that. So that's actually the biggest challenge at Samsung at this point. Okay. And then there's one more. So that William already mentioned our complexity, actually gate count, actually increasing, over the year dramatically. So, and then if you look at the each SoC, the number of IP inside is vary from like 50 to sometimes it's go even like 3 to 400. So if you want to actually integrate the 100 of IP efficiently without actually making any mistake, actually that's a big challenge as well. Right?
So one of the things that intrigues me is when I did my first chip design a long time ago, okay, the project life cycle was about 6 to 9 months. And as far as I can make out, nothing's actually changed for us. That's still the same, right? But I designed a 1700 gate design in 6 to 9 months. Now we're doing 300 million gate designs in 6 to 9 months, right? So clearly the complexity thing is real. It's massive. The interesting thing is as well is it seems like William's company creates the problems, Brian has the pain, and we have to come along and try and fix it, right? So it's a good team, right? But I mean, it'd be interesting to hear. I mean, is 6 to 9 months? What kind of project timescales? I think project timescales are the thing that causes the most pain indirectly for everybody. I mean, is that something that people agree with? Is it do anyone have a 2-year project timescale? 5-year? If your military used to be 5-year, strangely they don't make chips anymore. Anyway, so the pain. So when we started looking at this problem, I'd say 5 years ago, what we heard was exactly the kind of things we see here. Hundreds of IPs having to be integrated in a very short space of time. The IP from ARM seems to be coming out on an ever-increasing rate, so you've got to get your designs integrated out there before the next generation comes along and you've got to do it all again. And a lot of times the challenge is you seem to be repeating yourself, but it seems to be almost as much work each time. So there's obviously an opportunity. I think William alluded to this in terms of people wanting to modularize subsystems, but even then, there's still a lot of rework done every time a new piece of IP comes along. It can be disruptive, and you have to throw away big pieces of your design and start again. Or the other challenge from a configuration point of view is, how do I know I've picked the best configuration? Right? You get so many options. We're going to talk about this in a bit more detail, but how do I know I've got the best configuration of my IP? I mean, Cadence sells IP as well. We have very configurable IP. So it's a very known problem, and that doesn't seem to be changing. It doesn't seem to be getting easier. Okay?
Shall we pose questions from the audience?
I was just wondering, you said that Cadence has a lot of IP and it's very configurable. Is the level of configurability increasing as the complexity of the IP increases? And what kind of levels of configurability are you seeing typically in an IP?
I think from an IP developer's point of view, you want to service the biggest available market for your IP that you can. And the way to do that is configurability. If you design the best IP for one particular customer, that may rule out a whole load of other customers. So I think it's natural that configurability is there. From what I've seen, it's increasing. It's not decreasing, right?
So I'll just come in on that one. And so, I mean, we do see a big range. I mean, there's some IPs that are essentially just have a few parameters that are set, size of cache, number of processor cores or something like that. And then you move up to things that are much, much more configurable, where you have something like the interconnect, where you've got no idea how that's going to end up when you supply the IP. It entirely depend on the SOC design. So you have to have a much, much more sophisticated system for configuring an IP like that versus a single block that may be parameterizable. I don't know, Brian, whether you want to comment.
Yeah. So at Samsung, what happened was that so we are in the mobile market. So the requirement from the customer actually changing a lot over the course of the project. So we happen to have spec changes during the chip was half built and the spec changes, and then so that's very common. And then we do need a methodology that's such that it incorporate the new IP or remove the IP during the actually project. And then so that's one of the challenges too.
So if there are any more questions on the challenges, we'll move on to the next section, which is really about this configuration and integration of IP. So I'm going to start this one off again. Sorry, folks. On this one, I think in terms of actually configuring the IP, we've moved to an adoption of standardization. So we're using the IP exact standard very heavily to reflect both the actually configured state, the configuration that's been selected, and a way of passing that around the various tools, be they configuration tools, integration tools, or verification tools that fit all these pieces of the jigsaw puzzle together. On the actual configuration of the IP itself, we really want to try and abstract away a lot of the details. That as the IPs get more and more complex, we're trying to embody the knowledge of the IP into algorithms that are helping with the configuration of that IP as a way of really attacking the complexity issue. And then you come on to the integration side, and again, using intelligent algorithms and so forth, you can help do what Brian was referring to with the changing specs and the iteration of designs, so that you can reuse a lot of the work you've done, the rules you've written, the algorithms you've written to construct and integrate these systems with minor variations, so that you can whiz through the design cycle a little bit faster. We're seeing design rules that the need to check that the configurations match, and particularly when you've set up two pieces of IP, are they able to talk together? Are all the interfaces match? Are their properties match? Stuff like that, along with the capability to show in a much more digestible fashion what people have set up, so they can, with better visualization, schematics, documentation that's generated for a configured design, to help people rationalize and discuss what they've actually designed. Then you come on to the problem of the modularization, people taking a total top-level design and splitting it into different bits for implementation, and to cross-clock on power domains. And some of this stuff is highly mechanicalizable, and so the auto generation from configuration steps is the way you want to go, so you don't have to do that manually. I'm going to pass over to Brian.
Right. So that so as a real developer, as I mentioned that we have a really complex design, and how we actually build the SOC, reuse the IP faster than before. So what we did is that actually we adopt the IP exec as our main actually standard to build any kind of the methodology. So if we look at the IP exec based methodology, what we can have about 5 categories. So, and then it's also the design flow as well. So first one is that whenever you have IP, actually we package with the IP exec. So by doing that, you actually reduce or remove a lot of communication between the SOC integrator and then the IP owner itself. So that it actually, IP exec has a lot of information already, and then they packetize it. And then once you packetize IP, then what happens is that now you deliver to the SOC integrator, and then they do the integration. So there's a very little actually communication between the IP and then SOC, the owners at this point. And then once we have actually the full SOC in there, then we actually start, inserting a lot of we call the system level IP, which is like, for example, the clock tree and then reset tree, which is not part of the IP, but is a part of the system. And then some of them are like testing logic, and then we call the DFT mux. And once we have that, then the last one that we are doing is that we actually generate the test benches automatically. So here we are also using the IP exec. So we are asking the Cadence and ARM that the package the UIP as IP exec. This one include the VIP as well. So once we have a VIP as an IP exec form, then we can rebuild all the test benches very quickly. And then the last one is that if you look at the IP exec standard, it forces you to enter a lot of information. So one of them are actually register information. So that if you have IP plus the SOC based on the IP exec, basically you can extract a lot of information and then put it in the document automatically. So for example, if you look at the system register, that actually occupied about 60 to 70% of your actual documentation. And then you can auto-generate them. So those are the kind of 5 steps that we deploy at this point. And then I think that we actually reduce the turnaround time, actually SOC integration turnaround time dramatically. And then this is not just a one-time iteration. Actually, we did a lot of iteration. Because once the spec changes, we respin the SOC integration. And then if there's actually some performance issues that we have to move around the IP, within the SOC, then actually we have to reintegrate all that. So we're going through all this process through the IP exec.
Brian, I'm just interested to know. I mean, I don't want you to give away company secrets or anything, but what sort of acceleration here are you looking at in terms of the IP turnaround time through using IP exact and this methodology? Can you give us some sort of indication about the sort of acceleration you might get out of that, either in terms of months to days or 20% faster or whatever? What are you looking at?
So at least we're trying to cut at least the front end design flow half. That's pretty much the goal. Right? But even more.
So the thing that fascinates me is that a lot of these things I think are written here are somewhat standard things you would do to improve productivity, abstraction and whatever. The tricky thing is changing the way we do things whilst you're actually doing real projects. So Brian is trying to do this, change methodology, change tools, change working practices, whilst also having to deliver products. And that's true for everybody. To change to a new methodology or adopt new technology, it's very tough if you can't take a step back and just do it as a separate step. And that's probably one of the biggest challenges is identifying. You can't boil the ocean. You can't change everything in one go. You have to identify the big ticket items that are really going to make the big difference and attack them kind of one at a time. So although I guess when we started looking in this problem space, we had lots of ideas about what we could do, it's not been possible to say, here are all the solutions all in one go, because no company out there is going to adopt them in one hit. It's too big a risk. And so what's actually evolved is an evolution from one methodology evolving into a collection of improved practices, new technology, methodology, standards that gets you to a better place. And when you add up all the pieces, you get a huge productivity gain. If you take each individual one, it may not look enormous because all you do is, by fixing one thing, you expose what is actually the next longest pole in the tent. So I think this is for me anyway, is why this is a long process. Building SOCs is seriously complicated, and you can attack individual things and come up with new technologies and automation and standards. And as we know, standards don't happen overnight. They also evolve over, sometimes at glacial speeds. They evolve to solve the problems. And sometimes you have to innovate away from standards and then roll it back into the standards to move it forward. And a lot of things that we've been doing are really that kind of, I think that's what we've been trying to do.
Thanks, Nick. So, I mean, just going to pause for some, if there's any questions from the audience you want to ask the panel. We got anyone brave enough to ask a question? Yeah. Nick says, can we answer it? Well, we're going to move on just to show you some of the things that we've done amongst ourselves to try and address some of these challenges. And I'm going to start with the IP configuration flow, an IP integration flow that we're, as an example of the sort of things you can do, basically around the IP exact methodology flow. And here I'm just going to show you the sort of things that you can do with this kind of methodology. So over on the left-hand side, you've got your SOC, a very simple graphic there. And what you're essentially doing is you're taking a lot of IP exact files, which literally run to tens of thousands, if not hundreds of thousands of lines of IP exact that are giving you lots of information about registers, interfaces, properties of the IP. You're extracting in a machine-readable form that information and using that to create a high-level specification, a detailed high-level specification of a particular IP or an IP subsystem that you're creating. You obviously need some user input describing, what they want. If it was an interconnect, they'd need to be describing what masters and slaves they're connecting up. But then you use an algorithmic mechanism for taking that high-level spec and actually, using inbuilt knowledge of the IP that you're configuring. You sort of have a press button way of generating the configuration that matches that requirement. And then having done that, you can run a series of design rule checks or checks to make sure that things match and that all the architecture rules are met or whatever. And then once you've done that, you can then move to generators that will actually generate all the outputs on a push-button method. And I've got one more slide on that, showing the sort of inputs and outputs. And over on the left, you've got your architect putting in details. This is an example for generating an interconnect, which the architect's putting in is what he wants to connect up, the connectivity he requires in terms of bandwidths and latencies, if he's got any special architectural constraints, things like clock, voltage, power domains, things like that. And then from that and all the database of information about the IPs and the construction rules and so forth, you can then generate all the required outputs that Brian was referring to in terms of RTL, test benches, documentation, machine-readable documentation, and control strips to move into the implementation flows and so forth, including, of course, IP exact descriptions themselves to feed into the further down the flow. And importantly, a lot of data that can be used to report on things like achieved latencies through the interconnect or maximum bandwidths and area of logic and stuff like that. I'm just question to the panel. Is there any more we want to point to or audience want to make on IP configuration before we move on to the verification aspect of this puzzle? So I think I'm going to hand over to Nick on this because this is more your speciality.
So, as I mentioned a minute ago, the way we've sort of attacked some of the SOC challenges is really by focusing on very specific, if you like, apps. There's a whole range of things. I think that's the difference if you look at verification of an SOC compared to verification of an IP block. An IP block, it's kind of self-contained. You can build a UVM test bench. It's a specific set of things you functionally verify. In the SOC space, it's a very fragmented space. There are some things you want to do that UVM can address. There are other things that UVM can't address. And you need specific apps in different spaces to address those. So what I wanted to do is just give you a brief outline of one of the apps we've built that really is looking at how we can build automation technology which can, in this particular case, apply to one particular aspect, but that we're looking to apply beyond that to the whole SOC. Now, one of the challenges with SOC integration is, as we mentioned, a lot of the IP that you integrate is very configurable. It could be third-party ARM IP that's very configurable. When you assemble it all together, how do you know it's going to A, function correctly, and B, perform? Because, functional verification will tell you transactions get from A to B, but they won't tell you how fast they get from A to B. And a lot of work is done early in the SOC design space on, say, TLM and architecture analysis, performance analysis, but ultimately when you assemble a bunch of IP, you want to go back and validate that the performance is what you expected it was going to be. And the only way you can determine this accurately is with RTL. So one of the applications that we've developed really looks at automating test benches around AMBER. So if you're familiar with ARM IP, AMBER is the umbrella under which all of the various bus protocols that are ARM related live. There is a whole range of protocols, and we can automate test benches that will connect to any AMBER interface and cover if you like, the point of injection of transactions to the point of exit. And when you want to explore and validate that this IP is working correctly, you need to model traffic in some simplistic way to check that the QoS, the quality of service, is actually operating correctly. So very typically, this is a kind of test bench you would want to build, and you might want to build it in lots of different configurations.
Nick, can I ask you a question? So what are the sort of problems that people would discover with this kind of test bench tool?
So you can be very basic problems. For example, if I've connected one of the clocks up incorrectly in an IP somewhere, functionally it may still work. An interconnect IP will transfer data across it regardless of whether it's got the right speed of clock. But you wouldn't know from functional verification whether you'd connected the right clock up, but you would immediately know if you did bandwidth checks. Okay? So that's one kind of configuration, very simple configuration issue. It gets more complicated because it may be that you've not configured your QoS correctly. You may have set one of the master's priorities to be in the wrong range, and in certain circumstances it either gets starved of data or another master gets starved of data. So that's a much more subtle problem that requires debug, but again you need to configure traffic to roughly model your real use case for it to make any sense. Okay.
So Nick, quick question. So that if you do the performance analysis, a lot of times that you have to deal with random traffic and then very long traces. So that do you actually enable all this through the emulation or Palladium?
Yeah, so the tool works with both simulation and acceleration. There are some of pieces of your SoC will run in simulation in a reasonable amount of time. It may take 30 minutes, an hour, a couple of hours to run some of it. But if you really want to run things like GPU traffic across multiple frames, you need to run on an accelerator. There's no other way you can do it. So we do support both models. But the test benches are very different that you generate.
I was going to turn it over to Brian to say, what sort of uses do you think you would make of something like this sort of capability? Would not particularly this. I don't want to, presuppose that you're using this particular tool, but in terms of the test bench, what are the challenges there for you?
So right now that the performance section analysis is sort of the headache, because we have a really short design cycle, and then the kind of measuring the performance in the pre-silicon time frame is very difficult. So that the one of the advantage of the IWB is that it has a pre-made actually the template that we can use for the performance analysis. So that's actually very decent actually experience.
So let me just give you examples of how you might use some of the automation technology. Why SOC challenges are slightly different from a typical IP challenge. And a lot of it is to do with the different points in the integration cycle that you need to apply either test benches or performance analysis. You could be looking at just an integration on the left here of maybe it's a combination of ARM interconnect IPs. It could be a coherent interconnect combined with a non-coherent interconnect, and you want to just validate early in your project whether that delivers the performance you need. You can do that very early. It's a test, because it's a test bench that's still pretty complicated. You can have tens of bus interfaces. Being able to automate the creation of that is very helpful. It gets worse as you integrate more of the SoC. Firstly, you might want to integrate the real DDR controller and get real cycle accurate memory performance measurements. And beyond that, you might want to do the full SoC running on a hardware box, maybe even running software tests. You might want to do an operating system, bring up, and then run some benchmarks and actually measure the performance then on Palladium. And so this is one of the challenges, is you need to be able to create test benches for these different use cases.
Actually, what I want to emphasize is that the automation that the Cadence bring in, actually, they saves the design cycle a lot. So from my experience, that we try to minimize the SOC integration and then test bench generation time, so that we have enough time for the verification engineer to do their real job. Right now, that what I see in the previous project, that they spend a lot of time to debugging the very silly mistakes, and then they don't have enough time to actually debug the real cases. So automatic test bench generation is pretty important.
So you want to have the engineers actually working on the difficult problems, architecting a performance system.
I think all engineers want to work on the difficult problems and not the mundane stuff. I don't know. That's the way I think, anyway. So with Interconnect Workbench, this is one of the new apps we've developed in the last few years, which uses automation based on IP exact. So we need metadata on the left, so IP exact. In some cases, customers don't have IP exact, so we can take in spreadsheets, whatever the customers have. but we take that metadata and then at the push of a button generate a complete test bench. Now, this gives you the ability to use test benches where you wouldn't otherwise put in the effort of developing them. When they've got hundreds of connections, it's a lot of work. If you can do this in half a day, get a complete test bench and run tests, it gives you a whole different perspective on the kind of things you can explore and analyze. As you can see here, there's two flows, one through simulation and one through acceleration. The key difference is in the kind of VIP that you can use in acceleration. It needs to be synthesizable VIP if you're using it in an accelerated flow. In the simulated flow, you use simulation-based VIP, which is not synthesizable. But ultimately, you can generate data which at the end of it allows you to look at bandwidth and latency analysis on any of the use models I showed you earlier. So the intention here is to illustrate that from IP-exact, as IP-exact becomes more and more prevalent in the SOC integration space, this is one example of automation that we can bring to you to help solve your particular problems. The list of challenges we showed earlier, we're looking to try and create more apps that actually address more of those challenges as we go through and as we work with partners.
Thanks, Nick. So we're going to pause for questions from the audience. Somebody out there must have one. It's an opportunity to quiz the panel on anything you might want to quiz us on. That's brave of us.
Nothing? No one's...
You're not offering good enough prizes there, Sean.
Oh, I know. Not enough prizes.
Well, at that point, I think probably is our chance to say thank you very much for attending this afternoon. I was, just to, not that you'll have much difficulty spotting it because we're directly opposite the ARM stand, but behind you, you'll be able to see some of the technology that we've been talking about this afternoon in terms of the core link IP and the tools for configuring it. For those who are too shy to ask questions, the panel will just be hanging around here for a few minutes to see if there's any questions you want to ask us one-to-one. Many thanks.
Thank you so much. And stick around, and we're passing out raffle tickets for our iPad Mini drawing at our 5:30 presentation. So for Nick Heaton and William Orme and Brian Choi, thank you so much.